Today, we will be discussing charged particles. The best examples of charged particles are protons and electrons. Protons are positively charged, while electrons are negatively charged. Typically, we see protons in the nucleus of an atom and electrons orbiting the nucleus. With charges, like signs always repel and opposite signs always attract. One interesting thing is that the nucleus of an atom is composed of protons and neutrons, but the protons don't repel each other. How does that work? The answer is the strong force. This is what holds the nucleus together. Relatively speaking, of all the forces that exist, the strong force is the strongest, hence the name. The electrostatic force is the force between two charged particles that causes them to attract or repel. The equation is F is equal to kQq over r squared. This looks like a fairly complicated formula, but it's really not that bad. K is the Coulomb constant, equal to 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. Q is one of our charged particles, and uppercase Q is the other charged particle. R is the distance between charges 1 and 2. Let's look at an example. Particle A has a charge of 1.6 times 10 to the negative 19 coulombs, and is 3 nanometers away from particle B. If the charge on B is negative 1.6 times 10 to the negative 19 coulombs, what is the force between the two charges? Here I have a picture of our example. What exactly do we already know about our problem? Well, we already know both of our charges and our R value. We also know that the force is going to be attractive because one of our charges is positive and the other is negative, and opposites attract. Looking at the equation, we have F is equal to 8.99 times 10 to the 9, this is K. Then we have both of our Q's, 1.6 times 10 to the negative 19. And on the bottom, we have 3 times 10 to the negative 9 squared. This is 3 nanometers squared. Plugging all this into a calculator, we finally get F is equal to 2.56 times 10 to the negative 11 newtons. This isn't a very pretty answer, but that's what happens when I try and come up with the examples off the top of my head. Let's talk about the signs. Did you notice how I left out the negative sign when solving the equation? The reason is that in electrostatic signs are just a convention. This means that the sign will tell you if a particle is positive or negative, and if it is moving to the left or to the right. But we can actually do that on our own. We know from the problem that the force will be attractive because the particles have opposite charge. So we can leave the signs out of our calculation and then decide at the end if our force is positive or negative to determine which direction our particle moves. Our particle will be moving to the right because it is being attracted to the particle that is on the right. In fact, if you did include signs in this calculation, you would have gotten a negative answer and found our particle to be moving to the left, which is incorrect. So what does our answer actually mean? Well, what we found is the force of particle B acting on particle A. That is why we report our particle to be moving to the right. We are talking about particle A moving towards particle B. If we wanted the force on particle B from particle A, we would get the same numerical answer, but the sign would be negative. Particle B moves to the left because it is attracted to particle A. Let's do a quick review. We have positive and negative charges, where like signs repel and opposites attract. The force from charged uppercase Q onto lowercase q is F is equal to kQq over r squared. We leave signs out of calculations and determine the direction our particle moves at the end. Let's take a break from all the math and do an activity. This is called the levitating balloon. You'll need a balloon and a wall. Build up the charge on the balloon by rubbing it on your shirt or your hair. Then try and stick your balloon to the wall. Can you get it to stick? Now, can you explain how the balloon sticks to the wall? Well, rubbing the balloon on your shirt transfers extra charge over to the balloon. We will say that it's a negative charge, but this is an arbitrary choice. Technically speaking, we don't know if the charge is positive or negative. We just know that it is an excessive charge. So we can conclude that it is a negative charge just because that's what we want it to be. Now our balloon has a negative charge. All of those extra electrons are trying to get as far away from each other as possible. When you stick the balloon to the wall, positive charges in the wall will be attracted to the negative charges in the balloon. The wall is now considered polarized. It has positive charges on one side and negative charges on the other, so each end of the wall is charged, but the wall in general is neutrally charged. The force between the positive and negative charges is what keeps the balloon from falling. You can go to this website for more information on this topic.